Have you ever just looked at a mountain range and wondered, could it be taller? I mean, is there a limit? Well, that simple question, it turns out, has a mind-blowingly complex answer. And it reveals these incredible hidden rules that shape not just our mountains, but entire planets. So here's the game plan for this explainer. We're going to tackle that question head-on. We'll start with the planet's own internal speed limit, then we'll jump to other worlds to test our theory. From there, we'll uncover this wild force called the Glacial Buzzsaw. And finally, we'll look at the very blueprint that every mountain is built from. All right, let's start with the big one, the question you might ask just staring at a picture. On the surface, it seems so straightforward, but as you're about to see, the answer takes us deep into the physics of our planet, and even beyond. It seems so simple, right? What's the absolute maximum height a mountain can reach? But before we can even get to an answer, we have to ask a different question. What do we really mean by high? And boom, right away, the whole thing gets complicated. You see, if you measure from sea level, yep, Mount Everest is the undisputed champ. But if you measure from the actual base of the mountain, way down on the ocean floor, Mauna Kea in Hawaii is actually over 1,000 meters taller. So suddenly, our simple rules aren't so simple anymore. Okay, so if a simple tape measure isn't going to cut it, where do we look? Well, to find a real universal limit, we have to go deeper. We have to look at the fundamental physics of rock itself. And this right here is the key. A mountain can literally get too heavy for its own good. Once it hits a certain height, the sheer, crushing weight creates so much pressure that the rock at the very bottom just can't take it anymore. It actually starts to flow, almost like a really, really thick liquid. The physicist Victor Weisskopf came up with this brilliant way to think about it. Okay, picture this. You're building a mountain, just stacking one layer of rock on top of another. Each new layer adds more and more weight. Eventually, you get to a point where the energy from adding just one more layer on top is enough to basically liquefy a layer at the bottom, causing it to squish out to the sides. The mountain physically cannot get any taller. And what's wild is that when you do the math, when you plug in the properties of common rocks like granite, you get a theoretical speed limit for mountain height here on Earth, somewhere between 10 and 14 kilometers. It's this beautiful example of how basic physics sets the very first hard limit on our world. So if this whole limit is about weight and the strength of rock, what happens if we change one of those things, like, say, gravity? To really test this idea, let's take a quick trip over to Mars. You know, Mars only has about 38% of Earth's gravity. Less gravity means less weight pushing down. So what do we see there? We see Olympus Mons, this monster volcano that towers around 22 kilometers high, more than twice as tall as Everest, and it fits perfectly with what the physics told us would happen. And this same principle, this battle between gravity and material strength, it scales up in a super fascinating way. It's the reason small asteroids can be all lumpy and shaped like potatoes, while bigger planets are forced into spheres by their own gravity. There's a tipping point, and it's got a great name, the potato radius. Yeah, scientists calculated it to be around 250 kilometers. Anything bigger than that, and gravity wins the fight, crushing the object into a nice, round sphere. It's the exact same physics that limits a mountain, just playing out on a cosmic scale. But hold on, the physics pushing up from below, that's only half the story. It turns out there's an equally powerful force working against mountains, one that doesn't care about the base because it attacks from the top down. Let me introduce you to the Glacial Buzzsaw. The core idea is that glaciers, which form high up above the snowline, are unbelievably good at erosion. They act like a massive, slow-moving saw, constantly grinding away at the peaks and stopping them from ever getting much taller than that local snowline. And the evidence for this is it's everywhere. When scientists looked at global topography data, they found this stunning pattern. It doesn't matter which mountain range, doesn't matter how it was formed, the biggest chunk of its surface area is almost always found just below the line where the climate keeps things snowy year-round. So you get this incredible feedback loop going. Glaciers saw off the tops, all that erosion removes a ton of weight from the crust, which then causes the whole landscape to bounce back upwards, kind of like a boat rising higher in the water as you unload cargo. That's called isostatic uplift. But as the land lifts, the peaks still keep getting ground down by the buzzsaw, which has the effect of concentrating the landmass right there in that narrow band just below the snowline. So we've got these two epic forces, one pushing up from below, the other grinding down from above, and together they set the limits. But what about the blueprint? What are mountains actually made of? And is there some kind of hidden logic to their very structure? Well, at the most basic level, all mountains are built from three ingredients. You've got your igneous rocks, born from molten magma. You have sedimentary rocks, which are built from layers and layers of old sediment. And then you have metamorphic rocks, which are other rocks that have been totally transformed by insane heat and pressure. These are the building blocks. But beyond the stuff they're made of, there's this invisible mathematical structure. And this is where things get truly mind-bending. There's a theorem from a field of math called topology that tells us that for any sphere, like, planet Earth, if you count up all the peaks, add all the valleys, and then subtract all the passes, the answer will always be 2. I mean, just think about what that means. A single peak has no idea it's on a sphere. A single valley doesn't either. But taken all together, their total numbers are fundamentally tied to the global shape of our entire planet. It really does feel like a kind of magic, doesn't it? So from the strength of a single piece of rock to the buzzsaw of a glacier, all the way to the elegant math of a sphere, we see that mountains are shaped by this whole host of invisible rules. And it just makes you wonder, what other incredible rules are out there, hiding in plain sight, shaping the world all around us, just waiting for us to ask the right question?